Hello and welcome back to Gaffy's Grinds. This is video 4 for leaving cert radioactivity, for leaving cert chemistry. The usual jazz, to make sure you eliminate distractions, close tabs, put away your phone. And this is video 4, so I suggest you watch number 1, 2, and 3 first, otherwise this isn't going to make as much sense. We've previously learned about the man who discovered radioactivity, and that was Henry Becquerel. And what he discovered was by taking a photographic plate, and he discovered this by accident. This was a plate basically brushed with a chemical called brushed with silver halide. And silver halide is a white substance until it gets exposed to light or other forms of radiation. And what Becquerel discovered by keeping his rocks nearby, he was a rock collector, he studied minerals, and what he discovered is that some rocks give off radiation. And this radiation was causing his photographic plates in a drawer to turn black. Okay, so this could now be used to detect the presence of radiation. This chemically realized these photographic plates. If you wanted to see if something was radioactive, you could put one of these plates nearby and you would expose them and turn them black if radioactivity was present. But there was still a problem. This didn't tell scientists how much radiation there was. It couldn't help them to put a number on it. Scientists would need to be able to work out what levels are present in different rocks. So they needed to put numbers on things. And when you want to put numbers on a measurement, put numbers on, we call this type of analysis a quantitative analysis. So scientists like to find out how much of stuff there is, not just if it's present. So quantitative analysis. So a quantitative analysis could help scientists to figure out how much radiation there was, and this would be very important for helping to figure out what were safe levels and help them to detect if they were trying to find new sources of radioactivity. It would be easier to figure this out. Now, so at the moment, we had no way of doing it until about 1928, when two scientists called Hans Geiger and Walter Muller created a device to solve this problem. A device that could measure radioactivity quantitatively. So what they did is they built this tube. Okay, so they built a tube. And inside the tube, there was a gas. Inside the tube, it was filled with a gas. And this was a gas that sparked, caused a spark every time a radioactive particle hit the inside of the tube. The gas would spark. What they then did was they put what we call an electrode in, which is like a metal rod, which was connected to a wire that was able to was brought to a device which was able to count the number of flashes, basically, or the number of sparks. It was able to keep a count of it. So at the moment, it would read 0, 0, 0, or it would be a very low number. So like 0, 0, like maybe 10. At the moment, there's no radioactive source nearby, and it's not 0. It's still going to read something, and we'll see why that is in a couple of minutes, but it's still going to read something. There's no radioactive source just nearby yet, though, so nothing's going to happen. So the tube was filled with a special gas that sparked every time an emission from a nuclear decay hit the side of the tube. So what happens is, then if you bring a radioactive source nearby, so this here is a radioactive source, what's going to happen is this is going to decay, and the radioactive decay, some of the particles are going to enter the Geiger-Muller tube, and once they hit the inside, they're going to create a spark because of this gas that's here. It's basically going to be like a little mini explosion, tiny little spark, little catch fire. And when that spark occurred, the current, an electric current, would be generated, which would flow along the electrode and down the wire, and it would be counted here. Each time a little current flew through, moved through the wire, it would send this counter up. So it would go up to 11, 12, 13, and so on. So the dial was able to show how many sparks had been detected. We call this device a Geiger-Muller tube, after the two people who found it. Geiger-Muller tube. Now we still use this piece of measuring equipment today. Okay, this down here was the counter, and it's able to count how many sparks there's been. If you can count how many sparks there've been, you know how much activity, radioactivity is going on. Modern, and they count it in counts per minute. Gives you a reading, counts per minute. So however many flashes per minute, that's what the screen will read out. Now, we still use this piece of equipment today, the Geiger-Muller tube, to measure radioactivity. And there's an optional setting on most of the new ones that they can actually give off a little beep every time an emission is detected. All right, so you need to know about this piece of equipment, the Geiger-Muller tube. So I suggest that you pause the video and make a sketch or a drawing of it and make sure you put the name after it. What does it do? It measures radioactivity. Measures the activity. How active is a substance? How many particles or how many decays are happening? Every time it happens, you get this little beep or this little count, and you can measure it. All right, so you can pause that, take that down. All right, and you're ready to do some practice questions. All right, so I want to pause the video and I want to have a go at those questions for me. Okay, so I want to write the answers in full sentences. Okay, a reminder that you should only be playing the video if you have done the questions. If you're not going to do the questions, then you're wasting your time. What is meant by an unstable nucleus? Well, unstable means that there are an unbalanced number of protons and neutrons, and the nucleus has too much energy, and it's eventually going to break up. The nucleus is going to break up. Okay, so you need to have that stuff in your answer. Okay, unstable means unbalanced protons plus neutrons, unbalanced number of them, too much energy, and nucleus will break up. So obviously I'm not writing a full sentence there, I'm just saying the stuff you should have in it. You need to make sure you have this stuff in your answer. Hopefully you remember that from when we did unstable nucleus. What names are given to the moment when an unstable nucleus breaks up? Okay, so we can have a radioactive decay. A decay event, or you could have like nuclear decay. All right, so those are the three. If you have two of them, I'm happy enough. What was the first method of detection? So make sure you're talking about the first method. So check your question always, is the advice I give. Check your question. What was the first method of detection of radioactivity? So if you haven't wrote about the first method, then pause the video and fix it now. Okay, the first method of detection was to use silver halide. Use silver halide, which turns black when it's exposed to radiation. So it's white, a white substance that turns black. What was the disadvantage of this method? It couldn't put a number on it, or it couldn't tell you how much radioactivity there was. Couldn't tell how much. It was not quantitative. So what does quantitative mean? It means to describe using numbers or to measure using numbers. That's what quantitative means, to measure using numbers or to describe using numbers. So the above method really only tells you, is it there or is it not there? That's what we would call a qualitative analysis. This is a quantitative analysis, means you actually measure it, put numbers on it. What apparatus do we use today to measure radioactivity? That would be a Geiger-Muller counter or a Geiger-Muller tube. Geiger-Müller tube or / counter, sometimes called by either of these names. Draw a diagram to show the apparatus, right? Well, I'm going to scroll back over to that diagram in a second and describe how this apparatus works. Okay, so to describe how it works, we've got a tube is filled with gas. That's the first step. The gas sparks when an emission, which is a particle which is kicked out of a nucleus, emission hits the tube, the inside of the tube specifically. This creates a current, and the current is carried to a counter. The spark creates a current, the current is carried to a counter, and the counter basically measures the number of sparks, I suppose. All right, that's it in a nutshell, as simply as we can put it. Hopefully you have an explanation, something like that. Bullet points are handy when you want to describe something like this, but a paragraph is okay as well, but you still have to have the main bits. So you should definitely mention a tube that's a tube and it has to be have a gas in. Yeah, you should definitely mention that you get gas sparks when an emission hits the tube. You should definitely say that a current is generated by the spark and it's carried to a counter. And then something about how the counter counts the number of sparks or counts the number of emissions, something like that. Okay, so if you have these key parts in your answer, then well done. If not, then you can pause and add the detail now. For number 7, make sure that you have this diagram. Okay, that's what you really need, that diagram there. And if you have that, well done. And I hope I don't have to keep telling you that you should be doing this from memory, not looking at the diagram you've already drawn and copied down. Hope that's clear at this stage. If you're used to my videos, you know what I'm looking for. Okay, so another little bit of stuff now. Okay, even if there's no radioactive source present, a Geiger-Müller counter will still register a certain level of activity. That's why, even before I drew the spark up here on the diagram, I still set the counter to like 10. Okay, so it wasn't 0 before the spark, the little spark. Still set it to 10. Now, this is because of radiation that exists naturally around us. Okay, so if I'm just going to draw a couple of things here. What I'm drawing here is I'm drawing a house. This is a house, and house has a roof, has a door, windows, and so on. You get the picture. And a house is obviously made of building materials, and building materials mostly come from rocks or stone. Building materials, just like we had Becquerel's, rocks earlier that were giving emissions. Building materials are made from rocks. They will give off some emissions. Building materials will give off a very low level of radiation. Now, it's not enough for us to consider it a threat, but it is going to be given off nevertheless, building materials. Now, the building materials, houses, are normally built on layers of rock. More rock here we have. Okay, so this here is layers of rocks underneath our homes. So this is another source of low-level radiation, rocks underneath our homes. Here is a person, and here they are holding their lunch or their dinner. It's a hamburger. Okay, so this here is food. Food, believe it or not, also gives off a low level of radiation. One of the most common sources of low-level radiation is the sun and space. You may have heard of something called cosmic background radiation. Okay, Stephen Hawking was a very big person when it came to studying cosmic background radiation. And basically, it's radiation that's coming from space and the sun when it travels to Earth. Okay, these are called cosmic rays. Again, these would cause the Geiger-Muller counter to register at a very low level, even though there's no major radioactive source present. One of the most common sources of low-level radiation is something called radon gas. So it's a gas that exists all around us at very low concentrations. Radon gas. It's usually released from rocks underneath the ground. And if this radon gas was to collect in high concentrations, then it would be something to be worried about. We would say that high levels of radon gas, that is dangerous. But at low levels, we don't really need to worry too much about radon. This is why most houses now, when they're built, have to have a radon test done to see if they're collecting in high concentrations in your home. If they are, then you need to do something about it. You need to install a special pump, which pumps radon out of the house, okay, because it's a major source of this low-level radiation. Another place where we can find this low-level radiation is in hospitals, for example, in X-ray machines. X-ray machines use basically gamma rays to fire radiation at your leg and measure it when it comes out the other side. And this helps them to make a picture of the bones of your leg. So on. So this is an X-ray. So obviously this is firing out radiation, and it's going to be a source of low-level radiation. X-rays. We also use radiation for treating cancer. So other hospital equipment actually fires radiation at like tumors to try and shrink them. We also use radiation machines to kill any microorganisms that might be growing on surgical equipment. So things like scalpels and tongs and stuff that have been used in surgery. Before they can be used in the next person's surgery, you have to really make sure they're cleaned, and like just throwing them into a sink and giving them a rub isn't really enough to ensure that all viruses, all bacteria, all fungi are definitely dead. So to sterilize, hospitals often use like radiation machines. They put them into a bag, they put them into this machine and fire radiation at them, and that just kills everything. So that there is another source of radiation. All this hospital equipment, building materials, food, rocks, the space and the sun, and radon gas. All of these create something that we call background radiation. Background radiation. So background radiation is radiation that occurs at a low level, and we don't consider it to be a threat. Background radiation. This gets picked up by a Geiger-Muller tube, and it's typically about 22 to 75 counts per minute on a Geiger-Muller tube. So if we're measuring with a Geiger-Muller tube and we just leave it out in our sitting room, there's no radioactive source present, but even still, you will still get a little bit of counting from background radiation. It's when the numbers go way above 75, then we would know, oh, there must be an extra source of radiation around somewhere. So that is background radiation. Okay, we don't need to worry about background radiation because it's at such a low level. It is there, but it's at a low level. It's not a threat to our health or anything like that. Okay, time to do some practice. All right, so what I want you to do is I want you to pause the video and I want you to write out this paragraph in full. I want you to fill in the gaps with blanks, please. Fill in the blanks with keywords, sorry. Okay, you should only be watching. If you've filled that out, filled in the keywords, answers are coming up. You should only be playing, checking if you've done them. Here are the answers. Let's check it. Okay, and a couple of questions to finish off. Pause the video, answer questions 1 to 4, please. Okay, number 1, why will a Geiger-Müller counter always register a certain level of radioactivity? That's because of background radiation. It's measuring background radiation. So if you said background radiation in your answer, well done. That's what it's picking up. There's 3 sources of background radiation. Okay, so hopefully you remember from the picture, we had food, building materials. One to remember for sure here is radon. We also have cosmic background radiation, radiation from the sun, X-ray machines, sterilizing machines, and radiotherapy machines for treating cancer. All right. We also have rock under the ground, which is a natural source of radiation. Some people say we should worry that background radiation harms our health. Explain why they are wrong. They are wrong. So this way you must begin by saying they are wrong because. So they are wrong because background radiation is at a very low level and it doesn't harm our health. Okay, background radiation is at a very low level, which is considered to be safe. It's around 22 to 75 counts per minute, which is considered safe, a safe level. Okay, so that's what you should be talking about there. Well done if you said that. What is background radiation? Okay, so background radiation is naturally occurring radiation from things like building materials, from cosmic rays that occur at a low level, which we do not consider a threat. Okay, so it's radiation all around us at a low level that we do not consider a threat. All around us, and it's not considered a threat. Okay. All right, guys, that's it. In today's video, you learned about how we measure radiation using a Geiger-Müller tube, and you learned about background radiation, what it is, and why we don't need to be too worried about it. That it's pretty standard. It's happening all around us all the time, and there's no way we can stop it. So you know, we've measured it. It's a pretty safe level. Humans have existed with this stuff for millions of years now, so I'm pretty sure we can feel, we can be comfortable enough with it. It's when the count goes up for some reason, that's where we have information that something is wrong, that there's a bigger source of radiation around that might cause the levels to be unsafe, and then we can do something about it. All right, guys, that's it. And I hope you enjoyed the video. I'll see you in the next one.